Hello everyone and welcome to the solutions video for Codeforces Round 776 Division 3. I know I didn't make any solution video for a long time. Well, I've been getting bad ranks and so I wasn't able to solve many problems. Today also I didn't solve many, but it was Div 3, so I was able to solve a lot. Who counts ABC anyways? Let's discuss the solution from A to E. That's what I have solved. So let's begin. Problem A. So in this problem, we are given a string. So like S1, S2, S3, these are the characters in the string. And what we can do in one operation is pick two adjacent characters and delete them. And what we want to do is reduce the string to a particular character C. Now, with one operation, two elements gets deleted. So the length goes from n to n minus 2. And we have to keep doing this until it becomes 1. So obviously, since 2 is an even number, the parity of length doesn't change, so obviously the length of the array has to be even. But what else? Well, let's say you're removing Si. Okay, there's some numbers before it and some numbers after it. Sorry, not removing but selecting. So let's say Si is equals to C. There's some characters before it and some after it. Now you would want to remove all these and all of these, so you want their lengths to be even. So for every occurrence of C in this string, we just have to check whether any of those occurrences satisfy this condition, that the length of the string to the left of it is even length, so we can remove it entirely, and the string on the right side is also of even length, so we can remove that also entirely. So let's see the solution or code. Okay, so take input and then loop. So for every character that is C, I'm checking that the left side has even number of characters and the right side has even number of characters. If so, if any of the characters satisfies these conditions, print yes, otherwise it is not possible. Okay, so next problem. In this problem, we are given a function f, which is, so fx, that is x divided by a, so this is floor division, plus x modulo a. Now a is fixed. Okay, remember that a is fixed and not x. I took x as fixed and it took a lot of time of me to go waste until I realized that x is not fixed, a is fixed. Anyways, a is fixed and x can vary from a given range L to R. And what we want to tell is, for all the possible numbers in L to R, what would be the maximum value of fx for all x. So we want to get the maximum of fx for all x belonging to L to R. So this is what we want to compute. So let's see what we get at so this is L and then this is R. So let's see what we get at R. Obviously this term will be maximized at R because R is bigger. So let's say we have 4 and 12 and we are dividing by 3. So since 3 is fixed, so 4 divided by 3 is 1 and 12 divided by 3 is surprise 4, which is obviously greater than 1. So bigger numbers give bigger quotient when divided, right? So that's pretty simple. So let's see. Remove. Okay, so R gives us the best, and now let's try to maximize this other operation as well, other term. So what does this give us? Let's say this gives us some value k, The maximum value for k is obviously a minus 1, because anything remainder a cannot be greater than a minus 1, because then it would circle back to 0 and 1 and so on. So let's say r gives us some remainder k which is less than a minus 1. Then what we can do is we can go step by step, not in the code, but step by step go, so as to eventually get this term to maximum. And okay, so we want that term to become maximum. And notice that when this happens, so the first time this will happen is when this term will decrease by 1. Okay, so let me take a numerical example. Let's say a was 9 and k was 5. So when we divided something by 9, we got remainder 5. So it could be 14. The number could be 14. Now when we try a number less than it, we'll get 13. Since we cannot try a number greater than it, we cannot increase the modulo from the right side. We will have to decrease it up to 0, right? So we go up to 9, and 9 divided by 9 gives us remainder 0, right? So this is remainder. And then one step before that would give us the optimal value for this, right? And let's see how our r by a has decreased. Our r by a has decreased by 1 here, because these whatever the quotient they gave, let's say q, this will give a q minus 1. So and every value before this will give us something worse quotient. And since this is already giving us the best remainder part, it is one of the best options. Another best option seems to be this, because quotient is high, right? So what we can do is try the rightmost element, which is r. If it is giving us a remainder a minus 1, then that is obviously completely optimal, because the quotient term and the remainder term both are maximized. However, if it is not a minus 1, then we can try the element, let's call this p. We can try element p, which gives us remainder a minus 1 at the cost of one loss from the quotient part. And since remainder was a minus 2 or less, right? So remainder was less than equals to this value. So the new remainder that we're getting, which is greater than this by at least 1, will obviously cover for the loss in remainder. And so the answer would be this. So what we can do is, let me reiterate, we try this. If it is giving us the best remainder, then this is the optimal answer, which is r, right? Because r by a, because the quotient term is already maximized. However, if it is not giving, then we're going to try the first number going to the left of it, which gives us the best remainder, and then that would give us the best answer. They could be the same. In case this was giving a remainder of a minus 2, then the remainder increment will accommodate for the quotient decrement. And obviously we have to check if p exists in the range. So let's see the solution, or the implementation rather. Also, please subscribe. Okay, so take the input. So x is the remainder, which I named k there, and this is the answer for r. Now I'm gonna move to the left x plus 1 times, because that would give us a minus 1 remainder. Because let's say I had 8 as r and a was 5, remainder is 3. If I move 4 times, I'll go to 4, whose remainder with 5 is 4, because remainder goes like this. So 3 2 1 0 4, 3 2 1 0 4. It's cyclic. So yeah, if that happens, I'm gonna take r by a plus r modulo a, because r has been increased, and I'm checking that r is still in the range. So that is something you had to keep in mind. And that was the solution for B. Now the solution for C. Okay, so what is this problem? So first of all, they introduced to us a term. What is that term? Nested segment. So an array of segments. So a segment is represented by L and R, right? So L1 R1 is the first segment, L2 R2 is the second, and so on, right? So Ln Rn. So a list of these segments is nested if the first segment, if let's say is this, then the second segment should be something like this. Its left and right end should be completely inside the previous segments left and right end and should not overlap. So L2 should be greater than L1 and R2 should be less than R1, and this should be satisfied for L3 and L2 as well. And so this is what a nested segment would look like. Now what we are given is, okay, so what we are given is m numbers on the number line. Okay, so A1, A2, A3, AM, and every number has some weight. So W1, W2, W3, Wm, and we have to make n nested segments out of these m vertices or points. And how we do that is every segment should start at some point and end at some point, and the ending points should be distinct for every segment. Now, so what we want is we want to make a nested segment and also want the sum of the weights that come in the endpoints of these segments to be minimum. So first of all, the main observation here is that let's say you want to make a nested segments of length 2 and you are given any arbitrary 4 points. Okay, you can always choose the leftmost and rightmost to make the first segment, and then the next batch for the next segment. And let's say you were given like 6 elements, then what you could do is do it like choose the next outermost ones and then choose the next outermost ones. So we can, out of any arbitrary points, we can always form a nested segment. And this is like a simple 2-pointer, right? We're going, I is here, j is here. The first segment is considering the current ij points. This goes plus plus, this goes minus minus. So for any 2n segments, 2n points, we can form n nested segments easily. Okay, so what's the next part? The next part is minimizing the weight. How can we minimize the weight? Just pick the points which has the minimum weights. So pick the weights that are the least. So sort this array and then pick the first 2n weights. So, and m is always greater than equals to 2n. So a1, a2, an. So we are picking these segments. This is after sorting and then making a nested segment list out of them. So let's see the implementation. And in output, since you have to tell their indices, obviously we need to make a struct to save all that. So I made a struct called input, which stored the position of the point, its weight, and its index. I took the input, I sorted it by its weight, and then I added the first 2n vertices into a vector of pairs which has the first element as the position and the second element the index. I'm going to need index for printing the output. So now I sort this by the position, because position is the first element in pair, it will be sorted by that. and the W is just the sum of the weights for these first two n elements. I print that, and then I do a double pointer. I is in the starting, j is in the end. While I is less than j, I do this, right? I plus plus j minus minus, like I showed here, and then I print the index of the first element and index of the second element, which is shown in the second element of the pair. So that was it. Pretty simple implementation wise as well. And now I could have done it by using tuple instead of an input, but I think tuple becomes really hard to deal with. Like you have to use dot get, or otherwise you need to use structured bindings. So that's why I just made input. Now problem D. Okay, what is problem? D say we have an permutation 1 to n, a sorted permutation. So we have an array where ai is equals to I, and now a jumbled permutation is given to us. So something like 1 3 4 2 6 5. Okay, and how it got jumbled is described here. So whoever this person is did n operations, and what n operations were, so they went from 1 up to n, and for every operation I from 1 to n, what is being done here is we're taking the prefix I, so prefix of length I. So let's say we are at I equals to 3. For I equals to 3, let's say this was the array right now. So for I equals to 3, we're picking this thing, this prefix, and then we are rotating it by some arbitrary amount, and this is being done in order from I equals to 1 to up to n. And after this we get this array. Now we want to tell, is it possible to get this array after doing these n operations, and also if it is, then find out the possible order of operations, and if there are multiple ways, then tell the one with minimum sum of operations. So basically, not operations, the rotations. So at every operation there are xi rotations. We want to minimize the sum as well. So how do you begin here? Well, notice that the operation that happens at the first element doesn't really do anything, and this is actually nothing helpful as well. Now for 2, see that whatever the operation happens, it gets really jumbled up. So this information becomes entropy, like it becomes turbulent kind of. Okay, I'm saying random words. Okay, they are not random, but basically this ordered information that we had, that okay, this was rotated by some amount, is really mixed up with all the other information that comes after it, right? And if I just wanted to get what will be the effect, like if I want to figure out how much should I rotate, I can't really figure that out easily. However, if I look at the last element, the last operation, right? What happens in the last operation? In the last operation, for the first time, the element at the last, so let me remove this and rewrite it. So this is the initial, right? Now at the last operation, this last element moves for the first and last time. So if this element was present here, then that means that 1 2 3, a rotation of 3 was done in the last operation. Now we have simplified something, right? Now we know that how many rotations must have been done at the last operation. That was 3. Okay, and let's say uh, 4 was here. No, let's say 5 was here, right? If in the final array 5 was here, that means obviously it was rotated these 3 times, right? Because this is a smaller prefix than this, so this would have been rotated along with this. So that means 5 was also rotated 3 times and then it came here. So if I were to rotate it left 3 times, then I would reach at the state of the array where this last operation was not occurred. So move it 3 back, and now, so I'm basically rotating the entire array, and now 5 is here, and that means that uh, actually what this means is we have just circled back to the same problem with one less element, right? With just one less element, and now we do the same thing. I see from 5 how much do I have to go. So let me just erase this. Let me just erase everything. So 1 2 3 4 5 6 was here, but now after rotation 5 was here, right? So this was the state of the array after the last operation, and this is the state of the array before the last operation, right? And now notice that I would reach this state by 2 right rotations, 1 and then 2. So that means that in the answer we had filled that for the last operation we did 3 rotations, and now for this second last operation we will do 2 rotations. And now if I rotate the array to the left, the opposite of what this rotation happened, right? So if I do that, I will reach to a state where only these elements would have been rotated and these are at their correct place. So I just reached to its sub problem, and so I can just keep on moving to the right, I can just solve from right, keep on moving to the left, and I can always get an answer. Because see, I can get an answer for one part, right? I can always know how much I needed to rotate to get 6 from here to any position. And after that when I rotate the array, so it goes to the right? After that, when I rotate to the array by the same amount and consider only the next prefix, then it is the same problem. And so I can keep on doing it, and in the end the last element would be just 1. So this is what we have to simulate. N is 1e3 and sum of n is also 1e3, so we can do n square algorithm. So let's see my implementation. This is actually a pretty neat implementation, I think. So I take in the input and then I store the answer here. Now I go from the right. Obviously for the last element I don't really need to worry about rotations, because no matter how much you rotate it, it will always be at that position. So now I find the position of the element that has to be here. So that is I plus 1, right? N is at the last position. So I find its position, and then I check how much was it shifted. So let's say 6 was here. 1 2 3 4 5 6, right? 6 needed to be here, but it was here. So how much it was rotated by? 1 2 3. So I find that shift. Okay, and why I'm modeling it with I plus 1. I plus 1 is the length, by the way, of the current prefix, is because let's say 6 was here only. So then position plus 1 would be 6. So ideally I can do 6 operations as well and be just as good, but I want to minimize the operations, so I'm not going to do anything unnecessary. So for 6 basically, or I plus 1, I just want it to be 0. So that is the shift, and so I store that in the answer, and then I rotate the array. Now in this operation, array was shifted to the right by shift amount. Now I need to shift the next prefix by left amount, by the same amount shift to the left. So how am I going to do that? I just called a rotate function. You can do it yourself as well, but how the way rotate function works is, you have an array a1, a2, an. Let's say you want to rotate to the left I times. If you want to rotate that many times, then you specify the beginning of the array, the ending of the array. Now notice I'm not specifying end a but begin a plus I plus 1 because I only want to rotate the remaining part because I've already fixed the last element. Now I want to worry about the next prefix. So this gives me the next prefix, and then this represents the midpoint. Basically, if I want to rotate by shift amount, so I will take the element or the iterator which is shift distance away from 0 or the first element, and then what it would do is it would move it there. So the rotation happens such that the element at this iterator moves to begin, and we need end obviously in order to be able to rotate everything. So that is my implementation. Thanks to the constraints, implementation was very clean. Now rescheduling exams, the exam, okay, and there, oh, because we can reschedule only one. Okay, so there are D days, day 1, day 2, day 3, and day D, and there are exams at particular days like this. Now this quantity mu is the smallest rest day this person gets. So for the first exam, the amount of rest days is 2. For this exam, amount of rest days is 3. For this exam, amount of rest days is 2. And let's say there is another exam here, then the amount of rest days for last exam is 1. So, and of all these rest days, I take the minimum. Minimum is 1. So this is what we want to maximize. Okay, so I want to maximize the minimum amount of rest days. And what am I allowed to do? What I'm allowed to do is pick one exam and reschedule it to some other day, which should be in day 1 to D and should not overlap with another exam. And then I want to do it such that this quantity mu is minimized. Okay, so since we can only move one element, that means if there are too many places where the value of rest days is equals to mu, then that means I would not be able to minimize it much further, right? So let's see. Let's say this was like maybe 2, right? If this was 2, and let's say there was infinite space here, even if there was infinite space, I can move it as far as I can, but these will still remain intact, right? So I won't be able to do much. So it seems like for frequency of mu, so mu is just the minimum rest days. If the frequency of mu is greater than 1, then it is not possible to increase mu by any amount, but it is wrong. Why? Because you should obviously check for at least 2. Now if there are, let's say, 2 values of mu, right? Basically mu is the minimum rest days and it occurs twice. Now if it occurs twice isolatedly, I can move this or I can move this. They won't affect this. So in that case, I won't be able to do much. However, in the case where it is like this is mu and this is also mu, then maybe I can move this somewhere else, right? And then reduce it. Obviously moving this or this won't do anything. So okay, for 2 as well there is some chance, and for 1, if this is mu, which one should you move? And the answer is you should try both, because this could be something, this could be something, we are not sure, right? Moving any one of these could help us to get a better answer. But now where do I move it? Now this is a problem, because let's say these were the places where exams were, and let's say I move this, right? And if I and let's take something, yeah, let's say it was much further allowed. Okay, so now here's the problem, right? So one obvious approach you might be thinking is take this. Okay, like I said, we have to try both the elements, right, to the left and right of the mu. So I'm gonna try both of them, and so I'm gonna explain only for one of them. How do we move it? Now you might be thinking, okay, let's say if you're moving this away, right? If I'm moving this, then, and let's say this goes very far, okay, then I can move it somewhere here and get a better answer, which would be this. But that is wrong, because something else gets smaller. Okay, something else may get smaller than that, and that might affect it, right? So maybe this is like distance d, and maybe this is greater than d, right? So that means it would be better to move this. And now where to move it, and if there are too many places like this, so we are not sure. So how do we go about it? Well, let's say I moved it, right? Let's say I remove it. Now I have some new mu, which I'm gonna call mu dash, and let's say this is the value mu dash. Now I want to move it somewhere such that it is greater than equals to mu dash, and actually you don't even have to worry about it, because what I'm gonna, my approach, we don't have to worry about it. But if we want to move it, we want to move it to a place greater than equals to mu dash. Wrong. If you were going along, you should focus that no, there can be a better option. Maybe this place is not greater than mu dash, and this place is also not greater than mu dash. Maybe just moving it slightly towards the left helps us increase mu to mu plus 1. Okay, anyhow, now enough with the side tracking. Now let's discuss how to figure out where do we want to move this. Well, instead of trying to greedily move it, let's see if we can move it somewhere to satisfy mu greater than equals to some value x. Okay, why this? Obviously I'm trying to apply binary search here. Now if I want mu to be greater than equals to x, right? Now let's consider it removed. First of all these values needs to be greater than equals to x, and then where can I place it? I can place it somewhere here or here or here or here, right? So for all the places up to this point, up to the last day, where do I want to move it? If I'm moving it in any gap day, right, the best would be to move it at the center. And if I move it to the center, basically maximum length would be available to the left and right, and I'm just gonna want these to be greater than equals to x. So I can move it to some gap if that gap is greater than 2x, simply because let's say if this is a day and this is a day or 0, right? If I move the new exam here and x is 2, then this satisfies. So if a gap is greater than 2 times x, I can move my new element to that gap, and then mu will be greater than equals to x. Or I can try to move it at d and see what is the distance with the last element, right? Because this is a special case where we can move to the rightmost, and obviously just after removing this, we have to check that all these are greater than equals to x. So we can check for x. If we can check for greater than equals to x, then we can apply binary search on x, because if we can have mu greater than 2, if we can have mu greater than 4, we can obviously have mu greater than 2. So we just have to binary search on x while trying to remove for element 1 here and then trying to remove element 2. So let me show you the implementation. Well, so this function does that check. So if I'm given an array, now this array assumes that that element which I'm removing has been removed from the array, and that there is an element 0 in the beginning, because that eases up the implementation. So first of all, I check that the gaps are greater than equals to required. If any of them is less, then mu will be less. Then I try the edge case where I'm trying to put it at D, and the last element is a dot back. And obviously, if last element is 10 and D is 15, the rest case is not 15 minus 10, it is 11, 12, 13, 14. It is 15 minus 10 minus 1. That's why I have minus 1 here. So if this satisfies, obviously answer is true. Otherwise, I'm going to try to place it in between the positions. So this is 0, A1, A2, A3, AN. I'm going to try to place it somewhere. So I get the number of rest days, and if those rest days is greater than 2 times required, return true, just like what I explained here. And now let's see the bind search. So I take the input, okay, delete, remove. So I take the input, and then I try to find the smallest mu, which is mi. So I get the current mu for every element. If it is less than mi, I update it. I update the index where it is present, and I update its frequency. If its frequency is greater than 2, just print the current mu, because I cannot reduce it. This was actually not really necessary, but okay. Now notice that the only case for 2 as well, when I can do it, this was not really much necessary, but I just want to tell you guys that okay, this is an obvious observation that you should have made. Now for 2 as well, the only case in which I can improve it is when mu is like this, and for that I have to try moving this. But for case of 1, I'm trying to move this and this, so case of 1 covers everything. So first of all, I'm going to try to remove index, and remember index 2 is I minus 1, index minus 1, right? So first of all, I remove the one of the indices, and then I do binary search on the required value, which is mid here. And then if index 2 is not equals to 0, because I have a 0 as well, which is not an actual exam, I cannot remove it to be somewhere else, so that is an extra check needed. And then I just copy back the array because I had removed it. I erase the new index now, and then I binary search again, and then I print the maximum of the answers. So that was the solution for E, and these are the solutions I was going to be discussing, and we're done with it. So hopefully you found them useful. Leave a like, subscribe, and I'll see you next time.